All right, in this section, we're going to talk about two rules of probability. First one is the multiplication rule, and the second one is the addition rule. When we take a sample, we usually survey more than one person, right? Like a one person sample would be kind of silly. So we ended up taking multiple people or multiple items that we select. So the probability of those kind of events gets a little bit more complicated. So we'll talk about how to deal with when we have to take more than one item and how does probability gets affected. So this one is corresponds to book section 3.3. So let's start from an example. Suppose a student from the class is randomly chosen. Let A be student has black hair and B be student wear glasses. So some students have black hair, some students don't, some students wear glasses, and some students don't. So look, number one, what is the meaning of probability of A and B in this context? Well, notice it's A and B. It sounds like this student has to have black hair and also wear glasses. So if you have black hair but if you don't wear glasses, you're not in this particular set. And for the same reason, if you don't have black hair, you're not in the set even if you do wear glasses. So in order to be in A and B, it sounds like you have to have both properties satisfied. So this is the probability that this person has black hair and also wear glasses. This person wears glasses, right? Wears glasses. So that's what and means. So to calculate it, we simply count the number of students in the both of the set A and B, then divide by the total number, which is basically sample space, right? Sample space. So this question was when we were to pick only one person. Let's look at the next example. Suppose the following question is asked. What is the probability that two students are chosen with replacement? What is the probability that both students wear glasses? Okay, it seems like we are taking now two students. This situation can also be written as a form A and B. This is where things get slightly complicated. So let's say we're selecting now two students. Now I want to make sure that both students wear glasses. So let A be the first student wears glasses and B be the second student wears glasses. So this is a case where it's also written as A and B, but here we have two people. So A refers to the first person and then B refers to the second person. So if you have a case like this, so the verbiage is very similar. The first case, we're picking one person, but this person has to have black hair and glasses. So it's like one person satisfying two conditions. Whereas the second example, we have two people, right? And they each satisfy a certain condition. So in that case, when we are selecting a bunch of people or more than one person, we refer to it as a multi-stage experiment. So in that case, we have a formula to calculate the probability of first person being certain way and then second person being certain way. So this is done probability of A and B is equal to probability of A, so that's the first person, times probability of B given the first person. All right, I'm gonna kind of fast forward to, I'm gonna do some example. Let's go look at number 7. Helen plays basketball. For free throws, she makes the shot 75% of the time. She must attempt 2 free throws. Let's see the event that she makes the first shot, and probability of C is 0.7575%. And then let D denote the event that she makes the second shot. Also then means probability of the making second shot is 75%. The last sentence says the probability that Helen makes the second free throw given, I'm going to underline given, that she makes the first one is 0.85. So question part A, are the events C and D independent? I can already see that if she makes the first shot, the probability of second shot goes up to 85%. Normally it's 75%, but she makes the first one, then probability of making the second one goes up to 85%. So I noticed that the probability has changed. So then I can say they're not independent. They are not, because the probability of the second event was influenced by the first event. They're not. So this is important part. How do I mathematically show that? If this was a question on the exam or quiz, I'm going to say, I'm going to look at probability of D given C. I'm going to compare that number to probability of D. Back then, when we were looking at the formula, we had a formula probability of A given B is equal to probability of A. That means this is independent. This is how independent. This is how I show two events are independent. I have to show these two numbers are equal. Sometimes they're equal, sometimes they're not equal. In this case, probability of D given C, probability that she makes a second shot given that she makes the first one is 0.85. I'm looking at the last sentence. Basically, this is what last sentence says. Probability of D is normally 75%. So they are not equal to each other. So because P of D given C is not equal to P of C. Probability changed. That's why they're not independent events. Okay, so I have that. Let's look at the next question. What is the probability that she makes both free throws? Well, hint is make both free throws as multi-stage end statement. So she makes the both shots. That means she makes the first one and, emphasize and, she makes the second one. So she's like probability that she makes both shots. I'm going to rewrite that as probability that she makes the first shot and she makes the second shot. Because C represents the first shot, D represents the second shot. So according to our formula we just talked about, probability of C times probability of D given the first event, right? So probability of the first event times probability of the second event given the first event. Probability of C is given, it's right here on the top. It says it's 75%, so 0.75 times probability of D given C, that's given in the last sentence, is 85%, so 0.85. So if I do 0.75 times 0.85, what do I get? I get 0.6375, and that will be my final answer. So this was a case where the question says blah blah blah, both blah blah blah. I have to translate to something and something, because both means first and the second. Then I can use the formula we just talked about, multiplication rule. All right, let's go back to number 3. Sorry, I'm going back and forth. All right, here it says A, same situation, black hair versus glasses. What does A or B? I noticed it says or, so I'm going to highlight or there. All right, that means when it says or, it just means either you wear you have black hair or you wear glasses. So if you have black hair but you don't wear glasses, you're included in this group because it says or. For the same reason, if you do not have black hair but you're wearing glasses, then you belong to this group because it says it is or that. If you have black hair and wear glasses, you definitely belong to this group. So here I'm going to say you could either you have black hair or you wear glasses. You wear glasses, or you can be both. You can be both. So generally speaking, when I see A or B, you're gonna have a bigger, this results in a bigger event, right? So usually it's gonna have a higher probability. So generally speaking, when I see probability of A or B question, I know my answer is gonna be bigger answer. Addition rule is gonna be probability of A or B is equal to probability of A plus probability of B minus probability of A and B. The reason this formula works is maybe it's easier if you see like graphical way. It's called Venn diagram. Let's say you have group A, group B. Group A is people with black hair, right? Let's say there are 10 people who have black hair, and out of 10, 3 also wear glasses. So I'm gonna put 3 here. That's black hair with glasses, right? And then 7, just black hair, no glasses. And then let's say there's 5 people who have glasses but no black hair, right? So in this case, there are total of 7 plus 5 plus 7 plus 3 plus 5. So there's total 7 plus 3 plus 5, which is 15 people in A or B. If I calculate A separately, that will be 10, right? Oops. So I know there are 15 people in this event. If I just look at A, there are 10 people. 10 people are, they have black hair. If I just look at the people who have glasses, there are 8 people. So if I just do 10 plus 8, that will be 18. But I know there are only 15 who are in A or B. Why is that? Because that 3 in the middle, those people get counted twice. So I have to subtract that. Make sure there's no double count. So if I do that, there will be 15. So I'm following the formula here. 10 plus 8 minus 3, so I get 15. I could have just counted without looking at the formula. That could have worked also. But it gives you just alternate way to calculate probability. Okay, so number 5 is also mutually exclusive. I'm gonna kind of ignore that part. We're not gonna talk about that here. Same for 6. Again, whenever we're gonna we'll skip the mutually exclusive concept. Mutually exclusive concept. So whenever you see the mutually exclusive question, you can just skip. So I'm gonna have you work on number 7 and 8, and we'll meet back at number 9. All right, we're at number 9. I kind of want to go over some of the names. As you can see, there are 52 cars. Each row has 13 cars in it. So 13 cars for each shape. It's called suit. There are 4 shapes. Half of them black, half of them are red. The last 3 cars, those cars are called face cards because they have face on those cards. The first one, you notice there's an A on it, so it's called ace. And obviously the first 2 rows, these are black cards. The last 2 rows, the red cards. They're just colors, right? So let's look at number 9, part A. We're selecting cars randomly. And notice it says probability of black and ace. So I'm selecting one card. And then this card has to be black. And also this card has to be ace. So basically I'm looking at those 2 cards. That's it. So my answer will be 2 out of 52. Again, 52 is my sample space. And this event, black and ace, there are only 2 cards that satisfy this condition. So the answer is 2 over 52. Part B, it says red or even. Again, even numbers are 2, 4, 6, 8, 10. Okay, it's fine. So it says red or even. I notice this or type of question. So it could be, if you're a red card, you're good. If you're even card, you're also in. So there are going to be a lot of cards. So I can just literally count. Red card, there are 13. and 13, so there'll be 26, and then 27, 28, 29, 30, 32, 31, wait, hold on, 26, 28, 30, 32, 34, 36. So I can literally count and get 36. So 36 over 52 if you just count. If you want to use the formula we just talked about, addition rule, because it's the OR type of question, what I can do is, okay, the red cards, there are 26 red cards, right? So that's probability of the first event. Now I'm going to add the probability of the second event. Even number, there are 4 even numbers, 2, 4, 6, 8, 10. So 1, 2, 3, 4, 5 times 4 is 20. So there are 20 total even number cards. So far I have 26 red cards plus 20 even cards. If I stop there, I have 46, but I know there aren't 46 of those because there are a set of cards that got counted twice, which is red and even. So I have to subtract probability of red and even. I need to subtract that number. So how many are there? 2, 4, 6, 8, 10. Basically, they are red even card. So there are 10 of them. So I'm going to subtract 10. So if you calculate it that way, if you calculate that out, you'll get 36 over 52. So you get the same answer. So there are alternate way to do this OR part. I could have just literally calculated myself just by counting, or I could have used the addition rule formula to calculate. Let's do, is there a conditional probability? Nope. So here, let's do the last part or part H. When 2 cards are selected with replacement, what is the probability that both cards are red cards? Here, I notice they're selecting 2 cards. So in my head, it's like, oh, that's got to be multi-stage. Multi-stage experiment. Because up until then, all the questions were about picking 1 card. But here, now all of a sudden, we are picking 2 cards. If you play like Texas Hold'em poker, you'll know that you get 2 cards in the beginning. So this is actually more reasonable or realistic question. So multi-stage experiment, that means I'm using so in my head I'm already thinking, oh, this has got to be A and B multiplication formula. Probability A times probability of B given A. So I'll just keep that in mind. So question is, what is the probability that both cards are red card? Again, it says both blah blah blah. That means the first one has to be a certain way and the second one has to be a certain way. So this means I can rewrite probability of both red to be probability of the first one is red. That's like my A, times probability of the second one is red. That's like my B, given the first one is red. Alright, so I know it's kind of complicated for a simple question, but it is what it is. So probably the first one is red. Well, there's 26 out of 52 red cards. So the probability is just there. Times probably the second one is red, given the first one is also red. Here the question is, it says they're selected with replacements. So basically I look at the first card, I'm putting it back. So that means there are still 26 red cards left for the second pick, and there are 52 total. If the question says without replacement, then, so just side note here, if it was without replacement, then 26 over 52. First card is the same, but the second card is going to be only 25 over 51 because first red card is gone. That means there are only 25 red cards left over 51 total cards. So just the difference between replacement and without replacement. Okay, so I'm going to have you guys finish the rest of the worksheet, and this concludes this section.